today we're going to talk about nuclear reactions. So a nuclear reaction is when we have unstable nuclei and either they decay into more stable products or they will combine with each other to create more stable products. Nuclear reactions occur in two different ways, but both ways create a lot of energy. The first way that we are going to talk about is through a fusion reaction. And a fusion reaction is when two nuclei combine to form one product. So an example of that would be right here. So we have 4,2He plus 8,4Be, and it's forming 12,6-carbon. So if we're looking at this example, we know that it's a fusion reaction because we have two reactants. Now, reactants are going to be those things that are to the left of our reaction arrow, okay? And we only have one product. So because we have, and again, products are going to be those things that are to the right of the reaction arrow. So we can identify something as fusion if we have multiple reactants and it's coming together to form just one product. Now, this type of nuclear reaction doesn't really happen here on Earth. Instead, it happens in our stars, and we think about it happening in our sun. And the reason why fusion reactions happen in the sun and the stars is because they need a ton of energy to actually get started. We have to push these two reactants into another to form a new type of nuclei, a new type of nucleus, and so it's really hard here on Earth to actually get those nuclei to combine. But because the sun is really hot and there's a lot of pressure within the sun, fusion can actually occur. This is the energy that we get here on Earth based on the products of that fusion reaction. So if we think here, it creates a lot of energy. Okay, so then we have fission reactions. And fission reactions are the things that are actually going to occur in our nuclear power plants. It's what we create nuclear energy from. And this is when the nuclei decays into multiple products. This still does require energy, but not nearly as much as our fusion reactions do. And they still create a lot of energy, but it's more controllable energy. When we are looking at fission reactions, there's a few different particles that are going to be part of them. And depending on the particles that are part of them, we can further classify our fission reactions. So I'm just going to move this down so we have all of them. Okay. Perfect. So we have 5 different particles that are going to be present in a lot of our different fission reactions. So our first one is going to be an alpha particle, and its symbol is 4,2He. So it is basically the helium nuclei. If we think about this isotopic notation, the top number is the mass number, and based on what we've learned so far, this bottom number is going to be the atomic number. Well, in nuclear chemistry, we think of the top number still as the mass number, but the bottom number we think of as the charge. So an alpha particle is going to have a charge of +2, and it has a mass number of 4. And it is helium, because if we look up on the periodic table, the atomic number 2, it is helium. Okay, then we have a beta particle, and the symbol for a beta particle is 0, -1e, and a beta particle is just an electron. And if we think about the charge here, it has a -1 charge. Here we have a positron, which is 0, 1e, and it's the positive form of an electron. Then we have a gamma particle, which is 0, 0 in this upside down ribbon. And gamma is going to be a high energy light. And then we have a neutron, which isn't really a nuclear particle, but you're going to see them a lot in our nuclear reactions, and it's 1, 0n. And so we typically see them either hitting into nuclear particles to get a reaction started, or it's going to be used on the product side to balance out the mass. So we need to know a few different things about each of these particles. we want to know how strong they are and what we need to do in order to protect ourselves from getting hit by these nuclear particles. So an alpha particle is not very strong, so it has low penetrating power. In order to block yourself or protect yourself from an alpha particle, you only are going to need paper or air. So again, we don't really need a whole lot to protect ourselves. Beta particles are going to be a little bit more dangerous, so it's medium penetrating power. And so we need a little bit more to protect ourselves. Plastic, aluminum, or wood would be enough to protect ourselves from beta particles. Positrons, because it's just the positive form of an electron, all of these things apply to our positron also. So this medium penetrating power and then protecting ourselves with plastic, aluminum, or wood is also true for for a positron. Now your gamma is going to be your highest energy and the most dangerous. So it has high penetration power. And so we need something a little bit stronger to protect ourselves from it. And so this is going to be lead or concrete. That our gamma particles will not be able to get through. And like I said, a neutron isn't really a nuclear particle, so we don't have to worry about that for the neutron. These things you do need to memorize. So when we are thinking about our different nuclear reactions, we are going to have to complete the nuclear reactions, and those are kind of the problems that we're going to see for this unit. We're going to have to complete them, and then we're going to have to say the type of reaction that it is. So the examples I gave you are all going to be fission types of reactions, meaning that, again, we're starting with one reactant, and we're going to create multiple products. So when we are doing this, we have to make sure that the mass numbers on both the reactant and product side are equal to each other, and then the charge, or our atomic number, are equal to each other. And the way that you do this is kind of just balancing out your reactants and your products. So if we look here, everything on the reactant side is just one thing, and we have two nuclei that make up our product side. So again, reactants is to the left of the arrow, products are to the right of the arrow. So let's start with our mass number. Our mass number on this side is 210, and that should be equal to 4 plus some number. So in order to get that number, we would do 210 minus 4. You're kind of just setting up a math equation so that our missing number is 206. So that's going to be our mass number on the top, and then we do the same thing for our atomic number. So our reactant side, we have 84, and so far we have 2 on our product side. So we can do 84 minus 2 to give us an atomic number, or a charge, of 82. So now this is our isotopic symbol, 206 over 82, so we have to figure out the element that it is. So you're going to go to your periodic table and look up number 82, atomic number, and find that that is lead. So this would be a complete nuclear reaction. Now we can classify them based on the nuclear particles that we see on our product side. So if we look at our nuclear particles, we have an alpha particle, 4,2He. So we would call this alpha decay. Okay, in order for it to be alpha decay, there has to be an alpha particle on the product side. All right, next up we have 14,6 carbon, and it's forming 0, -1e, and then we have to figure out the rest. So if we look at our mass numbers, on our reactant side we only have 14, and then our first product has a mass number of 0, so if we do 14 minus 0, we get 14 as the mass number on top. Then we have 6 as the charge, or the atomic number, on our reactant side, and so far we have a -1 as our product. So 6 minus -1 will tell us that we need a 7 here. Again, just to make sure, our reactants have to equal our products. So 7 plus -1 does equal 6. So now we have to figure out the element that this is. So we have 14, 7. We can look up 7 on the periodic table and figure out that that is nitrogen. Again, we look on our product side to figure out the type of decay this is. This right here is a beta particle, so we would call this beta decay. All right, here's another one. So we have 238 on our reactant side, and we have 234 and 0 on our product side. So if we were to do 234 plus 0 is 234, and we can set our different sides equal to each other. So 238 minus 234 is going to give us 4 as our missing piece. And then here we have 92 is equal to 90 plus 0, so our missing piece would be 2. Now, 4, 2 should ring a bell in our brain, and that is our alpha particle. So we write He next to it. So for this one, we have actually 2 nuclear particles. So this would be alpha and gamma decay. In order for something to be decay, one of these particles has to be on the product side. So let's look at our last example. We have 38 on our reactant side, and that's equal to 0 plus some number. So that number has to be 38 in order to make it neutral, or to make it balanced. And then over here we have 19, and on the bottom we have 1. So in order to make this equal on our reactants and product side, this number would have to be 18, right? 19 minus 1 is equal to 18. Then we can look up 18 on the periodic table and see that that is argon. So we look at the nuclear particle, which is 018, and so we can call this positron decay.